Welcome back, everybody. When we left off, Neo's new CoffeeBot 5000 had given him a bit of a scare with some strange behavior. Today, we'll see how reinforcement learning can provide a path towards fixing the CoffeeBot 5000. Neo is so distraught by his new CoffeeBot that he calls the manufacturer. Something must be wrong, he reasons. Nobody would sell a robot that would trample puppies. Since Neo doesn't know anything about machine learning, it's a shock to him when the customer service rep tells him the CoffeeBot is working precisely as designed. It's a feature, not a bug, apparently. Neo is deeply unsatisfied. There must be a better way, he thinks. He starts out on a quest to find the solution to this problem, to develop a safer CoffeeBot 5000. As we will see today, there is indeed a better way. The narrow AI systems of the CoffeeBot can't handle the complexity of the real world. Reinforcement learning can provide a way for the CoffeeBot to learn the general strategies it needs for navigating its environment. In the previous lesson, we saw that the two common classes of machine learning algorithms don't really capture the essence of how humans learn. For instance, we don't need to see thousands of examples to differentiate a dog from a cat. Despite this, they are enormously successful, and therefore we shouldn't discount their utility. Instead, we should take the best aspects of both and combine them to make a new class of algorithms. That new class is reinforcement learning. We replace supervision and labels with a reward system similar to the way you would teach a child or pet. Positive rewards are given for actions that we want to reinforce, and negative rewards can be dished out for behavior we want to diminish. Unlike the case with supervised learning, we can generate our own training data. This is accomplished by playing through a game many, many times. We compare our actions to the rewards to see what types of actions lead to the best outcomes. By looking for patterns in these correlations, all new strategies can emerge. It's true that we have to play a game hundreds of times or more to get an effective agent, but this really isn't so different from how humans learn to play games. The upside is that we don't have to get this data beforehand. We generate it on the fly, which makes us much more accessible to the lone machine learning practitioner. In the CoffeeBot 5000 example, we saw that the bot exhibited some strange behavior because it was just a collection of narrow algorithms. It was no more intelligent than a common toaster. In its defense, CoffeeBot didn't know much of anything about its environment, and so it couldn't predict how its actions would affect the environment. Stepping on the puppy was unfortunate, but an inevitable side effect of this shortcoming. In reinforcement learning, we solve this by giving the agent some representation of the environment and allowing it to correlate that with actions and rewards. The content of this information is a critical piece of the reinforcement learning puzzle. In some cases, it can be obvious what to use. For Atari games, an image of the screen is sufficient. After all, when humans learn to play, Space Invaders for example, that is precisely the information they use. The choice of what to use as an observation of the state of the system is part of what goes into the design of a good reinforcement learning system, and something we'll touch on in later units. But the basic idea is that it should be the minimal amount of information needed to convey something meaningful. The entire reinforcement learning system can be summed up in a diagram. The agent receives the state of the environment and decides to perform some action. That action then changes the environment and causes the agent to receive a reward. The new state and reward is fed into the algorithm to determine what new action to take. In practice, some actions are taken randomly and some are taken to maximize expected future reward. When to use which strategy is what is called the explore-exploit dilemma and is the topic of a future video. But suffice it to say that some combination of both is really needed to achieve an optimal framework for picking actions. This framework is what is called a policy. It's an algorithm for determining what to do in any given state. Determining the optimal policy for a given environment is the main purpose of this course and what we'll spend the bulk of our time on. So, to fix our CoffeeBot, we can give it some model of the environment and allow it to play through thousands of simulations where we model various obstacles. Instead of teaching it to avoid each and every possible obstacle, it can learn that anything in its path is to be stepped around rather than on. It sounds simple, but as we will see in the remainder of this course, there is quite a bit of complexity there. To sum it up, reinforcement learning solves some of the major shortcomings of supervised and unsupervised learning. It gives the algorithm a model of the environment which allows it to predict how future actions can impact its reward. By playing through many games and generating training data itself, it removes the need for access to big data, which is a pretty big barrier for the machine learning practitioner outside of large corporations. In the next lesson, we'll talk about the required software for this course. From then on, we'll get to actually designing and implementing our own agents.